Okay, so preserve relationships in Bayesian models. And well, I think I'm probably just gonna go pretty fast here. Let's just say it's income. Sorry, so this slide here is important relationships. I just want to emphasize again the trade-off between utility and risks. Okay, so we are focusing on the utility for now because the modeling perspective of this is trying to capture the signal as much as we can, okay? And then hopefully we can do our best and then generate synthetic data out of it. And then, but too close could mean less privacy protection, so we need to strike the balance. But what we usually do, as you will see in this process, is that you're gonna go ahead with the model first. We're gonna generate synthetic data, and then we're gonna figure out how to evaluate the risk, how to evaluate the utility, and then look at the trade-off. And then if you want, you can use multiple synthesizers. We use synthesizers to refer Bayesian synthesis models, and then you can compare them. Like what I was saying earlier, maybe you can map them out, the utility profile and the risk profile on a two-dimensional map, and then you can decide what you want to do. Okay, so important relationships are important to preserve, of course, but preserving is one thing. Too close to the truth might mean less privacy protection, so we have to strike the balance. All right, so the example is relationship between income and expenditure. So you can always like plot them if you want, what kind of models you want to do. This is what, I mean, in a statistics class, that's what we call, what is it, exploratory data analysis, right? You want to figure out what kind of models you want to use. So we can, first of all, both of them are continuous, so you can do a simple scatter plot. Well, the relationship is not that clear, especially with the fanning situation. I mean, the fanny trend that you were seeing over here. So you can do what Henrik was suggesting earlier, especially with highly skewed data. You want to do some transformation. So I put everything, both of them on the log scale, I think, and then I plot them again. Okay? Still not perfect, but I think better than what we had before. You can sort of imagine the line going through. There's some variation, of course, but that's what the model is for. We are trying to capture, well, if you go through that line, let me just draw a random line here. Then that line, I mean, the position of that line, the variability of that will go into the regression coefficient, right? Beta 0 and beta 1, the intercept and the slope, but also the variation of each observation to that line hopefully will be captured by sigma if you're going to do the simple linear regression here. Okay. So, all right, so that means maybe we want to do a simple linear regression and review. If you're going to do simple linear regression, let's use yi to be the log income and xi to be the log expenditure. And you can write, so here I'm writing it through mu I, which is the mean, oh, sorry, there's a typo here. There should be an I here. This is for a normal model, where you have a observation-specific mean, right, mu I, and that mu I is a linear function of the xi, which is the log expenditure. So that's the predictor that you're going to put it in. So the parameters in the model, as we know, will be 3, right? Beta 0 is a parameter, beta 1 is a parameter, and don't forget sigma is a parameter. Okay, so again, mu I is the expected log income. It's a linear function of log expenditure through the intercept parameter beta 0 and slope beta 1. The interpretation of the two, I will leave that for you to review, but we need to estimate for both of them. And from the Bayesian point of view, they are parameters, they're random, so we give priors to them. And then we see how the posterior turns out, and then that can tell us a lot more about what beta 1 and beta 0 are. Okay. So I think this should be good. And to